notation to basically compare two different algorithms in terms of expressing the time complexity as a function of the input variable, input size, which is denoted by the variable n. So this example in orange, algorithm ABC, these are the time complexities. So it's 5n square, n square, and 100 times n to the 1.5. And you can see that in asymptotics, the third one is the best. And the first two are almost the same in terms of growing input size n. So we formalize this by Bigot notation. These were the examples. Insertion sort order n square. Faster sorting algorithms are order n log n. Binary search is the fastest algorithm. You will see it's order log n. So it is growing with input size, but very, very slowly. So usually the only thing you can get faster than this is constant time, which is order 1. But in order 1, you can do very few things. So binary search is kind of the smallest interesting algorithm. And this clever fib that we had computing f of n mod m, that was also around log n for m equal to constant, like 2024. Any questions till now? So let us see some more challenging algorithm design problems. So we'll see some examples which are quite difficult. These are difficult problems, especially to solve asymptotically faster. But as you see their solution and the design, you will learn some new things, more advanced ideas. So the first problem is max sum subarray. So here the problem is you have to write a program which takes input an array n integers, and in the output it has to output a subarray, which means that contiguous chunk of elements, say I to j, and the thing to maximize is the sum of the subarray. So subarray B say from I to j with max possible sum. Right, so what are the ideas for this? Yeah.
Will it not take another m as an integer to measure the length of the array?
I mean, even if it does, that length storage will only require log n, and it is n here, so you already have n integers. It's a much bigger space requirement than anything else. So all these things are trivial in asymptotics. I mean, order n plus order log n is still order n. So input size is slightly bigger than n. In fact, it will critically depend on how big the integers are, which is why in the previous class, when we were working mod m, we were saying that the integers are 0 to m minus 1, because that also requires space, obviously. Nothing you store on a computer is for free. So ultimately, everything you have to count. But in asymptotics, it will be hidden. So yeah, input size is n, just focus on integers to be very small. So it will be asymptotically n is the input size. In terms of that, how fast can you compute the max possible sum subarray of A? What is your first algorithm? Sorry? Yeah, so it will be well, n square will be quite fast. So the first idea is just double for loop, go over I, go over j, but then I to j also you have to sum up. So it's n times n times n. It's n cube algorithm. That is the first idea. Is that clear? Yeah, let's explain it. So this is the max sum the brute force algorithm. So this almost by definition what you can do is it's a double for loop. So for I going from 0 to n minus 1, in fact let me save space here. Just put I and j both here. So double for loop on ij, and then you need to compute the sum of this particular subarray. And you track the minimum sum. Maximum. And this closes the for loop. So in this pseudocode, what is happening is you are going over all the ij's. Let's say I is equal to 1 and j is equal to 10. This is one execution of this for loop, double for loop. So you have to compute the sum of a from 1 to 10. That particular interval you have to also find the value, right? So depending on how big the interval is, that much of sum, that sum you have to calculate. So that's another for loop. So there are actually 3 for loops. Okay, so 3 for loops means n cube. And as you go from one I comma j to the next I comma j, you can track the maximum sum. So whatever was the previous sum you store in a variable, let's say max, and next time when you get something bigger than that, then you update max, right? So track the maximum sum in some variable, let's say max. So that is a variable you can declare with minus infinity. So this minus infinity, whenever you see something bigger than that, it will get updated, and then it will get updated whenever a chance arises. So ultimately you will get the max sum. And obviously you can also store I and j. So when you update max, you can also update the I max and j max, right? So you will actually get the subarray as required. Is that clear? So let us just check its time complexity. So what is the number of steps of this maxsum brute? So number of steps, again up to asymptotics, is the outer two for loops. Going from 0 to n minus 1 each and independently. And the length of this subarray that you are currently at, that is j minus I plus 1. Right, so this is the number of steps which you can break down in computer instructions, but asymptotically this is what will be the lion's share in the complexity. So what is this calculation? Well, you have all crossed JE, so I guess I will not do that calculation. You can show that this is n cube. Okay. It's basically, I mean, NQ is also the max, so I, j go up to n, and j minus I also goes maximum up to n. So it's kind of n square times you are adding n. So you get n cube. And you can show that asymptotically it is tight. This will not be n square, it will be actually close to n cube. It's something like n cube by 12 or n cube by 24. So it will be constant multiple of n cube. So that is the time complexity. Is that clear? So the obvious question is, can you do better? In fact, there is a harder question, can you do it in linear time? Which is order n. So order n is very, very small. This is the minimum possible. It just scanning the array once, right? Once or constant many times. So in few scans of the array, full array, can you solve this problem?
Any index, it would be either the subarray before the index or the index itself.
So what is this value which you are trying to calculate for the index j?
And the value at that index, and if you can get a subarray before it,
Mm-hmm.
and subarray plus that index or the index, that's the maximum.
That is the maximum subarray that ends at j.
Just to take the sum.
No. You are giving the whole algorithm, but I am asking what is the algorithm computing? So at index j, what is the value which you are storing?
The value of at age,
Value of?
the array is in an age value, store age or the
No. So what he is suggesting will work, but the way to say it is that instead of using two indices ij, what you can focus on is just one index j, and you try to calculate the maximum subarray that ends at j. Okay, so forget about I, you just store, so create another array, we'll call it S of j, S of 0 to n minus 1, and S of j will basically store the maximum subarray ending at that index j. But even this is not clear why it will be linear time, because this is still single for loop, and then there are steps in the middle, so it may still be quadratic time. So we have to see this properly. So that is the second idea, which is a much smarter idea. So what if we reduce the number of indices? from 2 to 1. So we'll, instead of working with ij, which was requiring 2 for loops, we'll work with only j. Okay, that was the suggestion. So that is basically reducing the search space. But the risk always is that if you reduce the search space of your problem, then you may miss a solution. Right? So the cleverness is not in just coming up with this idea, but actually showing that even drastically reducing the search space from n squared to n, still the solution exists in this smaller space, right? So for that we have to work harder. So let's first define what we are trying to do with j, just j. So let us define Sj to be sum of the max sum subarray ending at j. Okay, so it is basically you are doing a max over all the i's with a fixed j. So j is fixed, and take all the predecessors or all the prefixes of j. So there are around n many prefixes. Out of them, what is the max? That is what Sj will store. Right. So it is a different, it's an array clearly different from Aj, because the values here will be could be bigger than Aj. So this is the new array. But how is this related to our original problem? So suppose you calculate all these values, S0, S1, dot, dot, Sn minus 1. What will be the answer to the original problem? Yes, still you have to take a max. So first you have to work hard to build this array, and then you have to take a max of this. So max can be found in a single scan of S, so that is not very costly. That's still within our linear time demand. So the only question left is, can we calculate this as S array also in linear time? That because by the definition it doesn't seem so. So we have to see how this is evolving as j increases. So let's see an example. So if your array A is, so remember that A has integers and they are unsorted possibly. So positive, negative integers, and also completely arbitrary order. So let's say it's 3, minus 5, 3, 8, 2, minus 4. So this is j equal to 5. Okay, so we are going from j equal to 0 to j equal to 5. So let's write down the values. So what is S of okay, let's start from here. So what is S of 0? Yeah, so S of 0 is 3. And what is S of 1? Yeah, so let's see this. Why are you saying S of 1 is S of 1 cannot be 3, no, because your subarray has to end at A1. So minus 5 has to be used. Yeah, so if you have to use minus 5, then either you just use minus 5, or it will be better to actually sum it up with the positive one. So it will be minus 5 plus 3, so that's the bigger value. So this value is actually minus 2. Yeah, I wanted minus 2, and then what is S of 2? Yes, so all the other prefixes are negative. They contribute a negative number. So it is better to just ignore them. So you use A3 only, which is value 3. What is S4? S4 is 11. You want to skip again 3 and minus 5. And so on, right? What is the next one? 13. And what is the last one? So we are going in this direction. So this will be 9. Right, so in this example, you can already see the evolution. You can see that when the previous value is negative, it is best to completely ignore it, as if that prefix did not even exist. And if the previous value is positive, right, then it helps to add it. So that is the algorithm. It's an algorithm to update SJ. So let me write down some basic observations. So first observation is that, well, okay, what is the answer to the original question, by the way? What is the max sum subarray of A? Yeah, so you look at these values and pick the max. So 13 is the answer to the original question. Array, I haven't given the algorithm. What's the algorithm? It's only an example. But yeah, if you are saying n square, good. So which means that the rest of the class wouldn't be a waste, because we'll show that it's order n. But for now, it's only an example. So in this example, you can see that the green values are is the evolution of SJ from S0 to S5, and it gives you some idea about how an SJ is actually related to the previous SJ minus 1, SJ minus 2, and so on. So what did we observe from here? So first is that if we have computed the S array, then we have solved the original problem. Then we can output max sum subarray of A in order n time. Right, because you just have to calculate the max of these green values. And yeah, so proof is just, I mean, ideally, whenever you will write a statement in your assessments, you have to give a proof. I usually skip the proof because it's obvious in the class, but you have to do it formally. So the proof for this is you just have to calculate the max. Because this max is equal to the max sum subarray. And what is the reason for this? Why is the max of these green values the max sum subarray of A? Yeah, so you have to show carefully that the search space is not being, the important part of the search space is still there. So the search space was for all ij's. So, and we are going over all the j's. So since we are going over all the j's, the correct j we also went over. And when we went over the correct j, say j star, in this case j equal to 4, when we passed j equal to 4, we had calculated the value of that particular I comma j, which is 13. Right? So that's the formal argument. Since each j appears in S. So the correct one also appears, and that gives you the value that you are looking for. So the Sj only gives you the max sum. What will you do for I? How will you calculate the exact interval? Did you see that in this example? What is the I for 13? Let's write that. Is it this? I equal to 2 and j equal to 4. Right, so you have to keep, if you want, you can keep track of the i's also. So as you are evolving S, you can have another array called I, big I, and the big I array can store the i's corresponding to every Sj value. Yes?
We can keep a suffix sum array, and in the suffix sum array also will have 13 in the I index I is equal to 2, and we can show that where the both values are coincident.
So are you saying that you don't need an extra array?
We need an extra array.
Yeah, so I said that extra array, call it big I, and the big I array will store the I value at big Ij. So what is the prefix starting point? That you can store in an extra array. So both S and big I array will give you the exact interval also, if you wanted. Okay, so hopefully you have understood now the major ideas in this paradigm, or in fact in this algorithm. So what remains is compute Sj in constant time. Given the earlier values. Okay, so as we were going from left to right in the example, if using the previous values, we can calculate the current value in just constant time, right, then n times constant will be order n, and you would have computed the whole array S. So you have to make this constant per iteration, right? So you are not allowed to use a for loop. You have an outer for loop going from 0 to n minus 1, but everything inside the for loop has to be very simple, just constant time operation. So this is the part which we have to now implement. If we can implement this, then it will mean that we have an order time algorithm. For the original problem of finding max sum subarray of A. Okay, so we are now, so the conclusion is subject to this question whether you can answer this yes or not. So for this we have to formalize how is Sj related to the, let's say, Sj minus 1, the previous values. So let us say that the max sum subarray ending at J starts with I, starts at I. So this achieves the optimum. So, I mean, obviously everything here is unknown, but the reason why we are setting this notation is to see what is the, how did I to j minus 1 subarray evolve and become I to j. Okay, so there were actually two options when you were at j minus 1. So one is and the other option is not use the previous part at all, so just stick with AJ. So when you were at j minus 1, say this this prefix I to j minus 1, P prime achieves Sj minus 1. So the maximum was achieved by I to j minus 1. Either you use that with AJ and get a bigger prefix, I mean bigger in length, or you don't, or you ignore it and you only use AJ, single element. Right? These are the two options. Is there a third option? When you were at j minus 1, was there a third option? I mean, at least in the example, you did not see anything else. In general, can there be a third option? Sorry, Sj minus 1. Sj, yeah, so that it will not change the answer. The maximum sum will not change. So can there be a third option which changes the answer, which gives you a bigger sum? Sorry?
An array is given with all constant, all negative in limits, you can take 0.
No, if all the entries are negative, you don't have 0 present. Then you have to take, then Sj will be equal to just Aj. No, so there is no third option which can give an improvement. This is what you have to observe here. Because so either you will take the singleton array Aj, or if you want something before that, the part before also has to be a subarray, and then you will try to maximize the sum there, right? So which is actually the definition of Sj minus 1 itself. Sj minus 1 exactly achieves that. It achieves the prefix ending at j minus 1, which is maximized. So either you will use it or you will avoid it. Okay, there is no third option. So this does not exist. So there are only two options. That's what you have to formally show. In fact, the statement already is the proof here. So to get Sj, either you use a prefix before Aj, or you don't. Okay, there are exactly two options. Now, why would you not want to use a prefix? If there is a prefix whose value Sj minus 1 you have calculated, what can be a situation where you avoid it? That's the only case, right? So the latter is done if and only if Sj minus 1 is negative. That's the proof. Okay. So you have only two options, either to use the prefix or use some prefix or not. But if you are going to use some prefix, well, you should then maximize that part. So maximum value will be given by Sj minus 1. And you will not want to use it only when that maximum is also negative. Because if you add negative, then your value further falls down from Aj. Right? So, and you are interested in the maximum subarray ending at j. So then it is better to live with Aj alone instead of adding the negativity behind. Okay, so that's the proof, and this gives you a very simple update. You just have to check whether the previous value was negative or not. If it was negative, you throw it away. If it was positive, you add it. So this is a constant time update. Yeah, let's write that important lemma. So this is the lemma which dictates how you will do the updation. So if Sj minus 1 is positive, then what is Sj? Yeah, you will use the value, positive value, and the new element Aj. and if this value is negative or even 0, then there is no point to add it. So then you stay with this element alone, the new element aj. Okay, is that clear? And as you can see, this is a very simple update. It's constant time as we wanted. Let's give the main point here. So in the first case, a I to j minus 1 extends to aij, and in case 2, eij minus 1 is modified to just aj. Okay, so this is how the max sum subarray is evolving. The previous one, I to j minus 1, either you can extend it by adding one more element, the new element, or you can completely forget about it and just get aj. So these are the two updates which you can use to also find the I values. So you can calculate the S values by the blue formula, and the black part also tells you what the I is. Right? So so as an exercise, you use this to also get the updates for I array. So maybe to calculate the I array, such that ij is equal to I with Sj equal to sum of I to j. Okay, so we want to keep track of small I also, because small I can change very drastically. In case 1, it does not change, it remains the same. But in case 2, it is completely forgotten. And it becomes what? So what is the update in case 2 for small I? Small I becomes j, and j minus 1 becomes j. Right? So the two endpoints, the starting point and the endpoint, are equal to j in the second case. And in the first case, the starting point doesn't change, the endpoint increments by 1. So you can keep track of small I in the big I array. So as an exercise, you also calculate this array in the same time. So you have both the maxsum and the subarray start endpoints. So everything can be calculated in linear time. So yeah, that's the clever algorithm. So let's write that. So take the array A, initialize S array to the 0th element, and do the for loop. So for j1 to n minus 1, if s j minus 1 is positive, then update, then extend the previous subarray. Else it's a singleton. And the final step will be just calculate the max of these of the S array. Say it is Sj0. So output these values. So output this J0 and the value Sj0. Okay, so this solves the original problem. You find the S array in order n time, and then you find the max of the S array once it is fully calculated. And you can also output as a bonus the J index, which corresponds to the max sum subarray. And if you also want the I index, then you can keep track of the third array, which is the big I array. So you will have ij and ei to j, which is Sj. Any questions? So this part, the for loop takes only order n time. And then you have a max which will again take order n time. Okay, so these are essentially two scans of the array. So in two scans of the array, you are able to calculate max sum, which is brilliant. So this is order n time. Okay, any questions? So the problem, from the problem statement or from the definition of the problem, it was n cube, right? But we have been able to make it n from n cube, which is a significant improvement in practice. Right? If you had a big array, cubic to linear is an incredible progress. Okay, so then I think we can stop. You can ask questions. We'll meet next time with a new problem.